So welcome everybody. Ladies and gentlemen, you likely heard the buzz around the blockchain. That is the popular name of the technology behind Bitcoin. It might look like a hype, but I can assure you it is not. The technology is here to stay. It is an exciting new technology to build systems that are auditable and executing business processes in a trust-minimized manner. That is precious, especially when interacting with corporations, trading partners, using distributed ledgers built on the blockchain technology. So what does it promise? I'd like to point you in this presentation towards the technological reasons of interest, and that are, in my opinion, auditability, network-wide consensus, privacy and compliance, and trust-minimized execution, finally, smart contracts. The blockchain is a data structure built for provable consistency. The consistency on a database, consistency check on this database is cheap to prove. However, it is flagged on different levels if somebody would attempt to tamper it. Tampering with it is practically infeasible. Let's review the database structures from the bottom. The blockchain is an append-only transaction log. It substitutes the ledger if we aggregate the transactions by the owner of accounts, which is the owner of the outputs. On the lowest level, we have transactions that reallocate their input to a set of outputs. The transactions are identified by their cryptographic hash. A hash function is mathematically a trapdoor function. It is easy to calculate in one direction, that is the data to hash, but it is quite infeasible to do the reverse, that is to find the data that would produce the hash or find an alternate data that would produce a same hash. Transactions are collected then into blocks. Blocks are also hashed with the same cryptographic function to define their identity, and the block refers to the previous block using this ID. The references define the chain of blocks and hence the name blockchain. Since the order of transactions influences the block's hash, their order is also fixed within the same block. And the global order of transaction is given by the chain of blocks. It is apparent that adding, altering, or removing transactions would change the hash of that block that it is contained in, and with that, the hash of all subsequent blocks. The entire chain would have to be recomputed from the point of modification to the latest block to present a new consistent state. By adding further constraint on the block hash, we can imply a significant work that needs to be performed, or blocks might be required to have a signature of validator, or so the verification is undeniable. And the transactions are hashed into the block's identity by ordering them into a binary tree called a Merkle tree. The value of every level of this tree is the hash of hashes on the lower level. This structure offers a significant advantage to audit, since the existence of a transaction can be shown in a compact proof, including the transaction and only the aggregated hashes that entered the tree path to the transaction. The compact proof saves bandwidth and also allows for pruning of history for transactions that are no longer relevant, since all their output is spent. The advantage against ordinary deletion in a database is that in a pruned Merkle tree, it preserves mid-states of the block ID calculation, hence it still proves that all transactions remained in the block were already there as the block was created. A pruned block is just as strong proving evidence or existence of a transaction as a full block. This proof of existence has very exciting applications. A transaction may hold a reference to external data and prove its existence in a compact manner, referring to the blockchain. Since blocks have a timestamp that is also part of their ID, the transaction would prove the existence of some external data at some past time point. Note, however, that only a full block history can prove non-existence of a transaction to a certain time point. Another very important property of the technology is a network-wide consensus. Blockchain is typically not maintained by a single server, but it is held in identical copies by nodes participating in a network. This makes the ledger that it substantiates, the distributed ledger, which is the primary interest of our work at Digital Asset. And achieving a network-wide replication was trivial if the nodes were trustworthy, operated by the same software. This is, however, not a realistic assumption, especially if we do replication across companies. Execution, on the other end, cannot be fully trusted because every single actor could be hacked. Such a failure should, however, not have a network-wide effect. The problem we face here is what is known in mathematics the Byzantine generalist problem. That is roughly how to achieve consensus in a network in absence of trust between actors. There is a limit to fault tolerance that can be seen very easily with the triangle chart on this sheet that shows you again general with two lieutenants, and you see if the lieutenant is faulty, then the message communicated to the, if the general is faulty, then the message communicated to the lieutenants is contradicting. And there is no way to solve this problem until the proportion of, the proportion of faulty actors is below one third. While above result is generally valid, Satoshi Nakamoto proposed an approach that works well in practice, adding an assumption that mathematicians usually avoid. And that assumption is that there is a computation, a work, without any shortcuts that nobody can reduce. And now if we require that every actor who wants to vote on the validity of a block performs that work, then we can compute a majority opinion of the network, a majority by computation power. And this brings the threshold for the honest majority to 1/2 instead of 1/3. Again, measured with computing capacity. While both approaches, the Byzantine fault tolerance algorithms and the Nakamoto-Consensus are valid for a practical solution, there is a trade-off between trust and computing power. The network with known actors could be operated cheaply and efficiently, assuming less than 1/3 of faulty actors, while a network without assumptions can use proof of work at less than 1/2 of computing capacity being dishonest. The combination of both approaches is a current subject of research and product development. Operating a shared ledger across companies is obviously superior in performance if we compare with proprietary systems connected via typical batch processes and reconciliations. Having a shared ledger, however, raises the concern of privacy between trading partners. The blockchain offers here a new security model. The solution is to keep identities that engage in transactions secret, not reusing keys. If implementing this, individual transactions reveal nothing about trading partners. And note the emphasis on individual transactions. Sophisticated data mining algorithms, however, could cluster the activity and gain some insight by time, especially if correlating the evidences with evidences available outside of the blockchain. For heightened privacy, therefore, so-called zero-knowledge proofs could be applied. A zero-knowledge proof, with a zero-knowledge proof, the transaction is partially encrypted. This disallows parties not involved to deduce the economics of the transaction, but they can still convince themselves that the transaction is in fact valid, although its content is partially unknown. There might, however, also be legitimate interest in trading activity by authorized parties, such as regulators, arbitrators, or legal actions. These uses can be addressed, for example, by deterministic key generation that allow a clustering of seemingly unrelated identities on the blockchain. The homomorphic property of the elliptic curve key generation supports deterministic identity generation without insight to the generation of associated private keys. This can provide read-only view while ensuring that transaction can still only be initiated by the owners of the identities. Accounts of a distributed ledger can also be owned jointly. This allows for support of arbitration or even automated transfer to a repudiation account. Note that the transaction validation is executed by all nodes autonomously, and while they update their own copy of the ledger. This means that those validation algorithms have to be executed with identical outcome on all nodes, so their database features, as enumerated in a consistency check, remain in sync with others. Nodes may not deviate from the rules without losing consistency, and especially not violate these rules on a case-by-case basis. The described execution environment is unique, since no one node on the network is able to override the rules. Therefore, the trust into a proper execution of the nodes is minimized. Revising, removing, or adding a transaction to the common history quickly becomes infeasible even for a bigger minority of faulty nodes. This new paradigm of execution is what we call trust minimized, and its application is countless. We are just starting to explore this huge solution space. A network-wide consensus building could be also too expensive for example, high-frequency trading. For scenarios where trading partners repeatedly trade with each other, we may introduce netting channels. They consist of offsetting transactions that are valid to be committed to the blockchain at the discretion of the trading partners at any time. They, however, doesn't have to. Instead, the offsetting transactions could be updated to reflect the new allocation of funds on a regular basis, and then flushed to the ledger once it is appropriate by a higher level business function. The challenge here is to establish a protocol whereby none of the trading partners gains an advantage by not following the rules or not following through the protocol to its end. Finally, validation rules. Observe that validation rules for a transaction may include more than just signature validation for the sources. It can require, for example, several signatures. It can use a set of signatures out of a set of joint owner. The evaluation rules may widen the context of the evaluation from a transaction to a block, thereby introducing time-dependent validity rules. Such rules enable, for example, automated escrow agents. Even external sources could be provided to the algorithms. So validation decisions could be influenced by them. Note that, however, introducing such an oracle reduces the trust into the source of that information. Now, the properties I enumerated are really enormous. We observe the birth of a new technology that might at first sight appear technically complex and wasteful. But if compared to the opportunities, it unlocks an area that is really worth of exploration. Let me finish with a quote from our CEO, Blight Masters, who said, "You should be taking this technology as seriously as you should have been taking the development of the internet in the early 90s. Thank you. I would appreciate questions.
Yeah. So, do we have any questions? We finished quite early, so we have time.
Yeah. So, can you come with some examples of, some real-life examples where you could use this technology?
I mentioned in this presentation, for example, proof of existence. Since the blockchain creates an auditable, near practically infeasible to manipulate structure, it is easy to commit a document or an existence proof of a document into the blockchain. I think alone this idea could revolutionize a whole range of current business processes, starting from patents to even eventually like registries. Yeah. What we currently work on is settlement processes, settlement of financial contracts. The blockchain itself is a settlement system, so it's very obvious to use for that purpose.
I have a question. If two nodes want to commit a transaction, they're different transactions, right, between two different partners. How do those things get sorted in the blockchain? How do you define, okay, which one goes first? Don't they both transact as the blockchain at the same time? Are there any mechanisms around that?
Well, the first question is whether the two transactions are really related. It means whether one is spending the other. If they are unrelated, then they could hit the blockchain both and could hit in any order since they are unrelated. It doesn't really matter. So the blockchain defines an order of transactions which is ad hoc if they are basically ad hoc if they are unrelated transactions. What is important is to order the transactions if they are related, because only if you order that, if you globally fix the order for transactions, can you decide whether a transaction was before another, and means whether the next transaction is an attempt to double spend some previous transaction.
So I always thought that when you add a transaction, you have to basically compute the hash of the entire block to be able to add it, right? Wasn't that the...
Well, if you compile a block, then you hash the transaction, and this hash enters through the Merkle tree into the hash of the block. This is the work that a miner performs in case of the Bitcoin network. So this is the process to include a transaction into the block. But this process only have to be done once, but checking that is very cheap and can be done by anyone else who is consuming the blockchain.
I'm reading that you're doing something called Hyperledger.
Hyperledger is a company that was bought by Digital Asset, just like my company, which was Bits of Proof. Okay. It's a different story. I was not. I'm in the meanwhile. Certainly, I'm looking at what they did, but I'm the responsible for building the distributed ledger on the technology layer of the company, and certainly the ideas that we saw with Hyperledger are entering these considerations.
Okay, I was just wondering what is the vision for Hyperledger, and I was also noting that it says that it doesn't have a currency, it doesn't have a cryptocurrency. And I was kind of interested in that choice.
Well, Hyperledger was meant to be an implementation of a Byzantine fault-tolerant algorithm. This is an alternative. As I mentioned, there are several alternatives how you achieve network-wide consensus. Practical Byzantine fault tolerance, which they did, is one of the alternatives. The question of having a currency, having a token, is completely unrelated to this question of how you build a consensus on a ledger. In case of Bitcoin, that currency also is used to incentivize that work, but that's a different story.
But then in Hyperledger, how do you incentivize the work if you don't have a cryptocurrency?
Well, the question is not Hyperledger. It's a question is, if you have a legitimate business interest to operate a distributed ledger, so there is an interest to settle transactions, that alone is sufficient to work with the system. You do not have to issue a token to incentivize this, because it's already incentivized by doing that economic activity on a more efficient manner.
But then that network is only operated by one company. Can you trust the network?
No, that's not the point. We do not think that these distributed ledgers would be operated by one company. That would contradict the notion of distributed ledger. We are developing software based on Bits of Proof, my previous software, and Hyperledger's ideas. And this software meant to be run by different entities, eventually be even compatible or interoperable with software developed by other companies. The point is we are creating a protocol on very similar to what Bitcoin did, creating a protocol to achieve consensus on a ledger and to maintain a structure, a blockchain structure with that very high level of consistency properties and auditability properties that I just described.
Yes.
Do you think it's going to be a private network, or is it going to be over internet, or how do you envision that's going to work? Because Bitcoin is an internet, right? I don't know a lot about it.
Well, I think there is place for both. Bitcoin is a network that operates in a very trustless environment. So I mean, where you cannot trust environment. That's why it needs a huge computing capacity to achieve consensus with proof of work. However, if you would operate a similar network of companies who know each other and have a certain assumption on the plausibility of collusion against each other, there you could operate a network which is less depending on a proof of work algorithm, but more depending on a Byzantine fault-tolerant replication.
That's what I thought as well. Can you somehow estimate how much that difference would be between a private network and a public network? So
how much the difference?
So in terms of we all know that Bitcoin network uses a lot of computing power right now, because it is operating in this kind of environment. What if we go to the other environment where we have companies that kind of trust each other, but they might not be always 100% sure whether the other one is going to act correctly or not? So how big a difference do you expect, or can you estimate somehow that there would be in the computing power that you could get rid of by using a private?
Well, I do not assume that a private network would achieve consensus by a proof of work at this point. I would assume that a private network would achieve consensus using Byzantine fault-tolerant replication. Proof of work might also play a role if you consider that if the blocks are in addition protected with some level of proof of work, that also adds a very objective level of security. Since consider that if somebody would want to forge a ledger, usually you do not have like an unlimited time to do this forgery, but you have a short time period. And through the aggregation feature of the blockchain that aggregates the work spent and that forces you to redo all the work that was done since the transaction that you probably try to forge, it means that there is an unbalance on how much is the effort needed to forge and how much is the effort needed to protect. So I assume that these kind of private networks will use both technologies with time, and we are currently exploring what is possible there.
Yeah. So any more questions? If not, it's just left to say thank you.
Thank you very much.